Okay. Particles moving according to the law of motion, S equals F of t. For t greater or equal to 0, t is measured in seconds, and S is measured in feet. We start by finding the velocity at time t. Notice that our position function is now a rational function. So you have to know how to take the derivative of everything. What do we use in order to take the derivative of that? We use the quotient rule, so let's make some space down here. V of t. After a while, you guys will actually get very, very efficient using the quotient rule, and we'll be able to start really right here. In order to use the quotient rule, I take the derivative of the top, which is what? 4 times the bottom left alone, which is t squared plus 3, minus the derivative of the bottom, which is 2t times the top left alone, which is 4t minus 10. I need more room. All divided by t squared plus 3 quantity squared. Now, I know that the bottom looks like it creates an issue for us. It really doesn't, and I'll explain that in a second here. But let's just simplify the top. So we have the velocity at time t is equal to 4t squared plus 12 minus 8t squared plus 20t. So now we can write our final derivative, which is the function for velocity, which, as we found, is very useful. It tells us the instantaneous speed at any given time. So we have the velocity at time t is equal to, what does that simplify to? Plus 12? Okay. Now, I want you guys to understand something about the nature of this velocity function, okay? And even the position function from the very beginning. Look at the denominator, t squared plus 3. I'm going to make a suggestion for you. The bottom is always positive. Do you agree that the denominator is always going to be positive? If you square a value, it's going to be positive, right? Our domain does not include imaginary, so we're working with real numbers. So you're going to have positive, and we're only plugging in positive values, right? Time is going to be positive. So you're always going to have something positive in the denominator. So that's really going to help our efforts here, okay? The question is, what is the velocity after 3 seconds? So how would I figure that out? Plug in 3. So velocity at time 3 is equal to, and before you do all the work, let's just remember, are we going to want to plug these into our calculator? So let's just do that right now. Sure. 4x minus 10. I will warn you, there are schools out there that they are saying, no calculators in your calculus class, in college. And I think that you guys have strong enough algebra skills that if I asked you to do that by hand, you'd be fine with it. But I think you should know how to use this as a tool. So, I now have both of them plugged in. The position function will be y sub 1, and the velocity function will be y sub 2. I suppose I could graph these if I want to. I think that the graphs are pretty interesting as we look at them. But that will give us time later on to kind of draw that stuff. If we simply go to the table, we could type in 3. If I type in 3, Do I want to focus on y sub 1 or y sub 2? Y sub 2. Y sub 2 is the velocity, and so I get 0.25, which is 1/4. And we have to write it. We have to write it as a rate. So I want to include feet per second. If you didn't get that, it's because you plugged the function incorrectly into your calculator. And you're going to have to look at that again. When is the particle at rest? When is the particle at rest? When the derivative is equal to 0. So I have to solve this. Now this is a little bit trickier, and this is what I want you guys to look through and see. I have to take this velocity function, or v of t, which is equal to -4t squared. What do we have, plus 20t? Plus 20t plus 12. Over parentheses t squared plus 3 quantity squared, and I have to find where that's equal to 0. Now think about this for a second. If it's equal to 0, I could just set the numerator equal to 0, right? I mean, if you were to write this over 1 and cross multiply, what would your new equation be? The numerator equal to 0, right? If the numerator is equal to 0, then the rational function is equal to 0, assuming that at that spot you can actually plug in a value, that there's domain there, and there is. So all we need to do then is set this numerator equal to 0. Well, what type of a function is that? The numerator, quadratic. How do we solve quadratics? It's quadratic formula or factor. This does not factor, so use the quadratic formula. Somebody punch it into your calculator. Well, you can take out a -4, but after that, it's not going to work for us. What is that? 0.54? Let's look at our graph and make sure that that matches up, everybody. If we take out our calculator, and if we go into y equals and only graph our derivative, again, we want to see where it's 0. So I'm going to press enter on that. And if I simply graph that, I know that my window is going to be a little bit out of whack here. I'm going to go a y minimum of -2, and I'm going to go y max of 5. I think that that's plenty in this problem. If we graph that, look what I have here. Okay, does it look like it crosses 0 at -0.54? And does it look like it's possible that this graph later crosses at 5.54? Really flattens out there a lot, but the fact is it very well could. So this graph does make sense. Are we concerned about negative time in this problem? No. So the only time where the particle is at rest is going to be for 5.54. Yes, if we go to our table and we plug in 5.54, we should come up with a number that is very close to 0, and we do. We get 3 times 10 to the -5th, which is basically 0. Because it's negative time, and in this situation we're not concerned about negative time. Okay, when is the particle moving in the positive direction? Again, if you remember the graph, I'm going to graph the velocity right here. We said that the graph looks something like, we'll pull it up again. You can see that shape, okay? And the shape looks something like this. It jumps up there, and then it comes down, and it kind of flattens out all the way to 5.4, and it goes through. So when is the particle moving in the positive direction? When the particle is moving in the positive direction is where the derivative is positive. Comment, question. Yeah, exactly. You can see that the graph, the derivative is above the x-axis from 0 to 5.54. So, and then it travels in the negative direction after that, right? So now we need to find the distance and draw a diagram. And that's the last piece I'm going to do here. I need to figure out where it starts. How will I figure out where it starts? I plug in 0. And if I go to my table, I can plug in 0, and I get 1.333. Is that what I want? If you look at my calculator, I don't have my original position function turned on. I need that. So I'm going to turn that back on. And now when I go back to my table, if I type in 0, so it starts at negative 3.33. Okay, that's where it starts. Now it travels in the positive direction until 5.54. Where's its location at 5.54? 0.36. Yeah. So it goes from negative 3.33. That's where it starts. It goes over to 0.36. And then it changes direction, right? That was at time equals, so this is at time equals 0. This is at time equals 5.54. And now we want to figure out where it is at time equals 8. So I go here, I plug in 8, and I get, so it just travels back to basically 0.33. That's about all it does. Not very interesting. Now could we figure out the total distance? Well, sure. It has to travel 3.33 to get back to 0. Then it travels an additional 0.36. And then it travels an additional 0.03 to get back to that 0.33. It travels in the positive direction from. So, you know, I'm just telling you that, you know, you understand conceptually, but then you got to be able to apply it to really any algebraic situation. Sometimes that causes concern. Question. Yep. 3.72 feet. Now, tomorrow, I am going to give you guys a lot of work time on this. We need to practice this in class, okay? Yeah, you could just add it on to yesterday's assignment. We're missing Anna today, so we could even write her a message. She could do numbers 3 through 6. Anna, you missed cookies. They were excellent. Did we save one for her? We didn't. Isabel, we did not save one for you either. Sorry. We're very sorry. Goodbye, YouTube Nation.